Section 6.6 is on page 275, is about the convolution integral, and here's your theorem. It says, suppose f of s is the Laplace of this function f, and g of x is the Laplace of this function g, that exists for s being bigger than a, and they're both bigger than 0. Then, if you take h to be f of s times g of s, that would be the convolution of h of t. So what this means, this h of t is the integral from 0 to t. Either you take f of t minus tau times g, or you reverse the order. You take f of tau times g of t minus tau. So keep in mind, if the integral of x squared is x cubed over 3 plus c, and if the integral of e to the x is e to the x plus c, the integral of x squared e to the x dx, keep in mind that does not equal x cubed over 3e to the x, or that does not equal, actually that's it, that's not true. But if I am to take the product of these two functions, and h would be this integral of the product of those two, where the function h is known as the convolution of f and g. The integral of equation 2, this is equation 2, those integrals are called the convolution integral. So you have an option every time. So here they're going to start off with number 4, and they want us to work backwards if possible. They're saying, find the Laplace transform of the given function. If you take the Laplace of this function f of t, so you're trying to figure out what is s of s. Well, f of s must have been, if you really think about it, this right here, they must have taken 2 factorial divided by s cubed, that's by 3, because this is representing t squared, and the cosine will give an s over s squared plus 4, I believe that's by 6, actually that's not 3, that's 2. By 2 and 6, let's just double check. 6 is a cosine, and 3, that was right. So this is by 3 and by 6. So actually it is 2 over s squared into s squared plus 4. That's really what must have been multiplied. And of course, in the next half of this section, you're going to work backwards. And again, if I apply the Laplace, this would be f of s. And you think of this without the shift again. Keep in mind how that works. When you took the Laplace, they took this and shifted by tau, or they took g and shifted that by tau, by tau. So here, this is, the sign will give a 1 over sine of t, 1 over s squared plus 1 squared, that is by 5. Oh, look at the 6 got knocked out of order. And the cosine will give an s over s squared plus 1. So this is s over s squared plus 1 quantity squared. That what must have been f of s. Now, if I want to work backwards, if I look at problem number 8, it says in 7 through 9, so I'm going to do one of them, I'm going to do number 8, find the inverse Laplace transform by using convolution, and that's you going backwards. If you take the inverse, this would be f of t. And what that would be, either the integral from 0 to t. So here you're looking for two functions multiplied. And you have a couple of options. You could say, you know what, I'm going to take that as a function multiplied by 1 over s plus 1. So either you say that's e to the negative tau, and this would be the cosine of 2, I didn't shift, 2, it should be 2t, but it's going to be t minus tau. You know what, let me get rid of that parentheses. There you go, that's much better. D tau. Or you could say, if you like, this is the integral from 0 to t, and you're going to shift the t, the exponential by t minus tau, and you're going to leave the cosine of t 2 tau d tau alone. Either way, it doesn't matter. And this is by 2. And this is by, what was it? Sine was a 6. And of course, this is by 16. You're allowed to do that. It is listed, if you look at the table, on number 16. There it is. So this is applying the Laplace. And this is applying the inverse Laplace. Right? F of t times g of t. Where one of these is shifted. And this is f of s g of this. There we go. So that's by 16. You could do that. So either or. Now, I could go in, let me see, yeah, I could do that. I wanted to do another example, a prime. Suppose f of s is 1 over s into s minus a. If I apply the inverse Laplace transform on both of those, I will get f of t to equal, and here, I could say that's 1 over s times 1 over s minus a. You could say this is the integral from 0 to t. Now 1 over s is really 1, and you could shift the exponential e to the a into t minus tau d tau. Or you could say, if you like, I'm going to leave e to the a tau d tau, and shifting a number by a value doesn't change anything. If you have y equal 1 and you shift it left or right, it stays the same. So either or, it doesn't really matter. And this you could say by 1, and this is by 2. So if I move to the next problem, and here we are, express the solution of the given initial value problems in terms of a convolution integral. There it is. If I apply the integral, if I apply the Laplace on both of those functions, that would be, and these are zeros if you notice, so you're going to just get 4 s squared f of s minus 4s plus 4s f of s plus 17 f of s, or you could have automatically said that's f of s times the characteristic equation, but in terms of s, not r. We did that too many times. And on the right hand side, you could say that's capital G of s. And you could say here that f of s is actually g of s divided by, and if I look at this, that's really 4s squared plus 4s. I was going to do that in one step, but let me do it in 2 steps. If I go on the side and figure out where this comes from, so I need to complete the square. If I take 4 into s squared plus s plus, take half of the middle number and square it. 1/2 squared is 1/4 plus 17. Since you added a 1/4, you subtract a 1/4. Since that's multiplied by 4, that's multiplied by 4. So this is really 4 into s plus 1/2 squared. And this is just a 1 plus 16. So I could do a couple of things. I could say this is actually g of s over 4 into s plus 1/2 squared plus 16. And now, if I really work my way backwards, well, let me see what I'm looking at. If I want to work backwards, I could say f of t is actually, and let's see how this works. And I could say I'm going to take the 4 out. And that will be what? If I take the 1/4 out. So this is the inverse Laplace of g of s times 1 over s plus 1/2 squared plus 4. So, a couple of things to really worry about. One, if I really wanted this to match, since this is a sine, I know that I'm going to take e I know I'm going to take g of tau because I don't know what g is. But this right here, if I take e to the negative 1/2, it should be t, but it's going to be t minus tau because that's what I'm shifting. That makes this 1 over s squared plus 4. So this is by 2 takes care of the shift. And this is a sine, and you know that the sine, you need to have what do you square to get that. So I need a 2 there, 2 on the bottom. I could multiply that by 2 and say, well, make that a 2 and a 2 right there. And that becomes the sine of t minus 2t. It should be 2t, but it's going to be twice t minus tau d tau. Of course, you have the option, and this is by 5. You have the option of saying that's 1/8 the integral 0 to t. You could have shifted the g function by t, right? And you could have said that's e to the negative tau over 2, the sine of twice tau d tau. Either of those answers will work. The back of the book gives one answer. If you got the other piece, so if the back of the book gives it this way, if you're off by a tau on one of the functions, that's acceptable. That's the same thing. It makes no difference. And suppose I want to apply the Laplace on this function. And here now things are slightly different. I am going to get f s squared f of s minus s times, in this case there's a 1 plus 0, that's this piece, plus 3 times s times f of s minus y of 0 plus twice f of s. And I know what the right side is. That is s over s squared plus alpha squared. This is by 6. And here, if I factor f of s out, I'm really looking at, you know what, 2 steps will do. No need to skip steps. That is s squared plus 3s plus 2. Again, the characteristic equation of that. What's left? I have a minus s and a minus 3, and that is s over s squared plus alpha squared. So if I move those to the right, I could say f of s is going to equal s over s squared plus alpha squared times, wouldn't that be s plus 1 into s plus 2? When I move those to the right, that becomes s plus 3 over s plus 1 into s plus 2, right? And if I really work this out and clean it up just a bit. So first I need to know here, if I clean it up just a bit, f of s is going to equal s over s squared plus alpha squared times, and let me see, where does 1 over s plus 1 into s plus 2 come from? Because convolution work on two functions multiplied, not three. If I clear the fractions, if I let s equal negative 2, I'll get 1 equal negative b, b is negative 1. And if I let s equal negative 1, that will be 0, a will equal a times 1 equal 1, that will be a 1. So this is 1 over s plus 1 minus 1 over s plus 2. My s's look like 5s. Okay, and here if I really work on this, I could say this is s plus 2 plus 1 over s plus 1 into s plus 2. Or you could say s plus 1 plus 2. It really makes no difference how you do this. And if I split this up even further, I could say f of s equal, if I distribute that in, that's s over s squared plus alpha squared times 1 over s plus 1 minus s over s squared plus alpha squared times 1 over s plus 1. Plus, if I split those up, that will be s plus 2 over s plus 1 into s plus 2 plus 1 over s plus 1 into s plus 2. And if I go a step further, so a lot of simplifications, the first two are done. Again, I'm writing all the steps down so you wouldn't be confused. And this I already found to be 1 over s plus 1 minus 1 over s plus 2. Well, you notice, oh yeah, that would have been easier. That gives me a 2 of those, right? So I can combine those into 1. And I could say, now that I know this, if I apply the inverse Laplace transform, I will get my f of t to equal, and let me, since I'm going to write two solutions, f of t is going to equal, and here again you have a choice. You could say this is the integral from 0 to t. You could say I'm going to take the cosine of alpha tau, that is by 6, and I could shift the e. It should be e to the negative t. It's going to be t minus tau d tau. That right there is by 2. This piece is going to give me minus the same deal, integral from 0 to t, cosine of alpha tau, e to the negative, it should be minus t. It's going to be t minus, those look the same. Oh, that's a 2. No wonder. I'm like, those are the same. What's going on? Okay, you guys should tell me that I made a mistake. That's going to be not 1. It should be 2t, but it's going to be, in this case, 2 into negative 2 into t minus tau d tau. And that is, again, by 6 and by 2. Not a problem. Now, this right here, when you do the integral, we know what that is. That is simply those two. Since that's a 2, that's twice e to the negative t, because they're not multiplied. This is by 2, and minus e to the negative 2t. Now, you could, if you want it, you could have shifted. You could have said, this part is the same. You could have said it's the integral from 0 to t, cosine of alpha into t minus tau, and not shift this, if you want, minus the integral 0 to t, the cosine. Of course, there are 4 different ways you could write this, and any of them is accepted. And I did put a t there, I just realized. A bit confusing between the t and the tau, just work with it. Okay, it doesn't look like a tau. Negative tau, there we go. D tau, and since I'm there, might as well let me wrap it up. Plus twice e to the negative t minus e to the negative 2t. There, either of those will do. There is the homework.